In this video, we're going to look at 3 examples of using the subring criteria to determine whether or not particular subsets of a ring are indeed subrings. In all 3 of our examples, we're going to use as our big ring the set of 2 by 2 matrices under their addition and multiplication. This is where M22 is the set of things that look like this, where all of the entries are real numbers. And in our first example, we're going to let D be the set of diagonal matrices. In other words, they have A and B on the main diagonal, and the off diagonal is made up of zeros. And again, A and B are any real numbers that you want to have. And the question is D a subring of the set of 2 by 2 matrices? Well, let's look at the 3 pieces of the Subring Criteria Theorem and apply them to this particular set. The first thing is that D is certainly not empty, since, among other things, the identity matrix 1001 clearly belongs to D. The second thing is I need to pick 2 arbitrary elements of D. So my first one will be the matrix A, which will look like A0, 0, B. And my second arbitrary element will look like C0, 0, D. And A and B both clearly belong to set D. And now my question is does A minus B lie inside set D? Well, that's easy enough to figure out. We simply look at computing A minus B. When we compute A minus B, we have this guy minus this guy. And when we do the subtraction, we have A minus C, 0, 0, B minus D, and that clearly is indeed a diagonal matrix. So the second property of the Subring Criteria Theorem is also satisfied. So now we have to move on to the third property. And the third property is asking whether or not the product matrix AB is inside D. And again, we figure this out by doing nothing more than the computation of the product of these 2 arbitrary matrices that live inside set D. So that's A, and this is B. And when we multiply them together, using the standard process for matrix multiplication, we're going to get a 2 by 2 matrix, and this first entry is going to be this row dotted with that column. So we're going to have AC plus 0, 0. So we're going to have AC up there. This entry is going to be this row dotted with that column, and that's going to be a 0 plus a 0. So we're going to have a big fat 0 there. This entry here will be this row of the first matrix dotted with this column of the second matrix, and you'll notice that that's going to be 0 times C, which is 0, plus B times 0. So that's going to be a 0 plus 0. That'll be a big fat 0. And this final entry is this guy dotted with that guy, and that'll be BD. And this particular matrix is clearly inside set D. So we now write a conclusion by the Subring Criteria Theorem. Set D is a subring of the set of 2 by 2 matrices. Well, let's see. Let's look at a second example. In this example, we're going to let D hat be the set of matrices that look like zeros on the main diagonal and anything you want on the off diagonal. So in set theory notation, that's what we would write this set as. And again, what I want to notice is the question is whether or not D hat is a subring of the set of 2 by 2 matrices. And again, what I'm going to do is I'm going to look at all three parts of the Subring Criteria Theorem. So first of all, D hat is clearly not empty, since 0, 1, 1, 0 belongs to D hat. So the first property of the Subring Criteria Theorem is satisfied. Well, the second one, I need to look at two arbitrary matrices of D hat. So I'm going to let A be this particular matrix, and that's clearly in D hat. And I'm going to let B be this matrix, 0, C, D, 0, and that's also in D hat. And the question is A minus B inside D hat? Well, A minus B is this matrix minus this matrix. And when we do that subtraction, we're going to get 0, A minus C, B minus D, 0, and that is indeed inside D hat. So the second property of the Subring Criteria Theorem holds. So we now look at the third property. Is A times B inside D hat? Well, let's just compute the product of A times the product of B. And again, we're going to get a 2 by 2 matrix. And this entry here is going to be this row dotted with this column. And when I do that, I'm going to get 0 times 0 plus A times D. So that entry is going to be A times D. And right away, I know that that's not in D hat. Well, if I go ahead and compute the rest of the matrix, I'm going to get a 0 there and a 0 here. And this particular entry here is going to wind up being this particular row dotted with that one, and it's going to be BC. The important thing is that since this matrix is not in D hat, that tells me that the Subring Criteria Theorem says D hat is not a subring of the set of 2 by 2 matrices. Now, it is important to realize that if you see immediately that this is going to be a problem, this is the only thing that we really need in order to conclude that D hat is not a subring. So it's okay to write down only this. This is all we need to write down in order to conclude that D hat is not a subring of M22. And that is something that's worth knowing when you're trying to show something is not a subring. Well, I have one more example that I want to look at. And this example involves a set of matrices that plays an important role in many areas of abstract algebra, as well as linear algebra and a variety of other areas of mathematics as well. The first thing that I need to do, though, is I need to recall the definition of a 2 by 2 matrix determinant. So the determinant of a 2 by 2 matrix is nothing more than the product of the main diagonal minus the product of the off diagonal. So the determinant of this matrix is AD minus BC. And Determinants are a little bit harder to generalize to larger sets of square matrices, but 2 by 2 determinants are very easy. And we're going to define a set that is called GL2 to be the set of all 2 by 2 matrices where the determinant of the matrix is not equal to 0. And GL2 is formally called the general linear group of order 2, meaning the size of the matrices are 2 by 2 matrices. And like I said, GL2 plays an important role in certain areas of abstract algebra. In a first course in abstract algebra, you show that GL2 is a non-commutative group under its multiplication. That's not actually going to play any important role in this particular class because we're looking at rings. So my question is whether or not GL2 is GL2 a subring of the set of 2 by 2 matrices. Again, I just want to look at all of the properties of the Subring Criteria Theorem. The first thing that I want to note is that GL2 is clearly not empty, since the determinant of the 2 by 2 identity matrix is equal to 1, which is not 0. So this matrix here clearly belongs to GL2. Well, let's see. The second property. If A and B belong to GL2, does A minus B always belong to GL2? Well, in this particular case, I want to actually focus my attention on this guy right here. In other words, I'm going to look at a specific example. I'm going to let A be this matrix, and I'm also going to let B be the same matrix, because then A minus B is the identity matrix minus the identity matrix, and that winds up being 0, 0, 0, 0. And it's important to realize that the determinant of the 0 matrix is a big fat 0. So A minus B in this case does not belong to GL2. And that's enough to say GL2 cannot be a full-fledged subring. So this is not a subring of the set of 2 by 2 matrices by the Subring Criteria Theorem. Property B does not hold for GL2. And we don't need to go any further than that. And that ends this particular video.